So let's begin. So Professor Chawla, so hope you are good to go with the questions, right?
Yeah. Do you want me to look at the Q&A and
No,
answer it, or are you going
we
to
have
read
the
the questions?
questions. We have the questions
Okay,
for
please.
you. Yeah. So
Yeah,
I'll
go
read
ahead.
out.
Yeah.
So let's start with the first question. I can see. So the first question that I can take, why semiconducting MX2 become metallic by simply charging the phase from 2H to 1T?
Okay. Yeah. I mean, the very simple way of looking at it is that when you look at the density of states of MOS2, the density of states is primarily determined near the Fermi level by the transition metal. All TMDs, it's a transition metal that determines the electronic properties. And so if you add an additional electron by doping with say lithium, then there is an additional sort of density of states that occurs at the Fermi level, right? So now you didn't have any finite states at the Fermi level in the 2H configuration. In the 1T configuration, there is this additional states that happen at the Fermi level. So you go from a semiconductor to a metal. The way the electron is incorporated into the d orbital of the molybdenum makes it such that the 1T or the 1T prime phase is a more sort of structural phase with this one additional electron. So MOS2 typically has two electrons in the d orbital. When you dope it, it has 3 orbitals. And so when you do the free energy calculations, you see that the having 3 electrons in the 2H configuration is structurally less stable than having 3 electrons in the 1T or the 1T prime configuration. So structurally, there is an energy gain by doing phase transformation with this additional electron. Electronically, it becomes metallic because you have this additional electron creates these additional states at the Fermi level.
Yeah. So in line with that particular question, so in the introduction part, MX2 is explained. One attendee is saying that he or she didn't catch 1T, 2H classes of semiconductor. Could you please explain this class? So maybe someone young researcher is asking
Yeah.
about this particular.
So the 2H and 1T are just crystallographic phases. So what it means is that, so if I go to one of the earlier slides, like this one. So you see, if you look at the unit cell, this is the trigonal prismatic unit cell. And if you look at this is the octahedral unit cell. So the 2H and 1T are just the crystallographic orientation of the unit cell, the structure of the material. Just like any material, there are stable phases and metastable phases. And so in the case of MOS2, the 2H phase is the stable phase, but the 1T phase is the metastable phase. But just like you can go from graphite to diamond at high temperature and pressure, you can also go from the 2H phase, the stable phase, to the metastable 1T phase by adding an additional electron, right? So, but in other materials, like niobium disulfide, for example, the 1T phase is naturally more stable, right? And the 2H phase is less stable. Because the niobium disulfide, if I go all the way back to the, I'll go all the way back here. So if you look at niobium disulfide, it only has the 1 electron, right? And so when you have odd number of electrons in the d orbital, you typically have a metallic phase that's stable. And if you have even number of electrons in the d orbitals, your TMD compounds tend to be semiconducting. So yeah, the 1T and 2H are just different phases, and different materials have different stable phases and different metastable phases.
Yeah.
I hope that's clear.
Yeah, thank you, Professor Chawla. We'll move on to the next question. So use of LiPS is very interesting. Have you measured any exchange current density or rate constant compared to simple sulfur and graphene mixture as cathode in the same electrolyte? This might support enhanced kinetics. Polysulfide shuttling still may be a big problem. So this is point.
Yeah. So no, that's right. So we've done sulfur reduction reactions with different polysulfide electrolytes, and we found that there's definitely enhanced kinetics. The polysulfide shuttling is mitigated a little bit in our battery electrodes, we think, because the adsorption of the polysulfides is appears to be quite good on these 1T MOS2, and the reason why is because the wettability of the 1T MOS2 electrodes is quite good to the electrolyte. So there's a combination of factors, I think, that improve the performance, the enhanced adsorption of the polysulfide, the better kinetics due to the fact that the electrodes are highly metallic, so the conductivity is high, and there's also catalytic activity directly with the metallic scaffold. And also the strong affinity of the polysulfides to MOS2.
Yeah, thank you, Professor Chawla. So there is a question around, particularly when doing colloidal synthesis, 1T can coexist with 2H phase. Are there colloidal synthesis methods to fabricate pure 1T MOS2?
Yeah, that's a very good question. So we've not been as successful at obtaining pure metallic 1T MOS2. We always have a mixture of 1T and 2H. It's not quite clear why, but I think that either the 2H phase, having a sort of a minority of 2H phase, maybe 10-20% of the 2H phase, I think helps to stabilize the 1T phase, around the 2H phase. But it is a challenge. I mean, one can make purely 1T phase MOS2, at least it's claimed, by chemical vapor deposition. But we've not been able to make 100% 1T phase MOS2 by colloidal chemistry yet. So that is a good question and an open challenge.
Yeah. So moving on to the next question, Professor Chawla. In the XPS of 1T MOS2, a peak of 1H phase is present as well.
Yeah.
Is it mixed phase? In most of the
Yes,
literature,
I mean,
yeah. So
sorry.
yeah. Please go ahead. We can take the second part later.
I'm sorry. Yeah, sorry to interrupt. No. It's so in the you always have the 2H phase or the 1H phase, as the questioner correctly puts it, present. In the TM, when we look at it in the TM, what you have are patches of the H phase and patches of T phase. You don't have complete sort of a random mixing of the two, at least not in our observations and what we've seen. But as I mentioned, purely 1T phase is not possible to make. So you always have the H phase that's present. But in the TM, these are sort of distinct patches of 1T, distinct patches of the H phase.
Yeah. Thank you, Professor Chawla. And I think the second part of the question is already been answered by you, that how to synthesize pure 1,2 MOST. And you have said that it's an open challenge. So we can move on to the next question. So from the stability, that is surface morphology point of view, which is better, 2D materials, sulfides or oxides? So
yeah, I think I mean, in terms of stability, these sulfides are very stable. So we and others in the community have done lots of sort of long-term experiments to show their stability in battery electrodes and catalysis and stuff. So I don't think there's an issue with that. Of course, in different environments, different materials will have different stability, right? So for example, in acidic or alkaline media, you might have better stability with sulfides or with oxides. So I think it really depends on the environment that you're using these materials in. But yeah, so there is no sort of universal answer saying that sulfides are definitely more stable or oxides are more stable. I think in these electrochemical environments, there can be lots of side reactions and other things that could happen. So I think yeah, in some instances, oxides may indeed be better than sulfides.
Yeah, so thank you, Professor Chawla. We have few minutes left, so we'll take a few more questions. Does the metallic crystalline MOS2 exhibit photoelectric effects that can, for example, be useful for hydrogen evolution reactions?
Yeah, so because it's a metal, there will not be any photocatalytic effect because you don't have you can't create really excited states because there's no it's a metal basically. So what you can instead do is perhaps utilize the 2H phase. So it's known that the sulfur vacancies in a 2H phase can be catalytically active. So you can then have a semiconductor with active sites. And if you can photoexcite the carriers into those active sites, then you can drive the catalytic reaction. But in the case of the 1T phase, because it's a metal, it would not make sense to use it directly as a photocatalyst. Of course, you can use it. One of the projects that we have right now is to integrate perovskite photovoltaics with 1T phase MOS2, where the perovskite is a absorber, and then the 1T phase is the catalyst.
Yeah, thank you, Professor Chawla. What are the challenges in the synthesis of thin films of individual phases? For example, MOS2 1T based thin films. So
yeah, I mean, I guess directly by CVD, he or she means. So it is quite hard to make metallic TMDs by CVD. I think there's a lot of efforts ongoing. But there are some nice works that from Peking University and in Singapore. Generally the metallic materials tend to be highly reactive, and so if you don't have the conditions right, it's easy to oxidize them or destabilize them. So I think that's the main challenge with working with metallic materials. I mean, in one way, I think that one reason, counter to that, one reason why these metallic phases are so useful is that in these kinds of electrochemistry applications, what you really require is something that is highly conducting, highly metallic, but non-reactive, right? That's why platinum is such a good catalyst. So that therefore, if you have something like MOS2 or a sulfide that is highly conducting, but non-reactive, right? Because it's a single layer with passivated electron. So it's from that point of view, it's quite reasonable that these materials would work in the kinds of applications that I discussed. Now, to synthesize large area from CVD has been a challenge, and it's not quite clear why. But I suspect that it's because you have to have a pure environment free of oxygen to grow these things.
yeah. So thank you, Professor Chawla. We have 2 minutes left, and again we have lots of questions coming in. But I'll seek your permission to take the last few two questions.
Sure.
Are you? Yeah, thank you. So, can the MOS2 electrodes show similar rate performance in supercapacitors with solid gel electrolytes?
Yeah, that's a great question. I mean, we haven't tested them with solid state electrolytes. Of course, it's difficult to know whether the material will work with a solid state electrolytes because solid state electrolytes themselves require some research, and so integrating them with into a device poses its own challenges. So it's not quite clear if the device limitation is coming from the electrodes or from the electrolyte itself. But as solid state electrolytes improve, I suspect that we'll be able to test those properties, and we hope that they work just as well.
Yeah. So I think we are running out of time. I'll take the last question. How does the actuation performance compare the CNT graphene based actuators?
Yeah, so I think the crucial thing here with the actuators is that because we have this very large capacity, the capacity is driven strictly by intercalation and deintercalation. We have this very large expansion and contraction of the electrodes, and so that large expansion and contraction is what allows us to do get this really robust and actuation. So I think that's really the key. And so I think the performance, at least in terms of the modulus and the strain and things, seems to be a little bit better than the actuators with graphene and nanotubes that have been reported. But I could be wrong. There could be better reports out there.
Yeah. So thank you, Professor Chhowalla, once again on behalf of audience.